Welcome! We're going to be talking about damage and prevention of radiation. Radiation is the energy given off by something as either waves, often called rays, or particles. For example, the sun gives off some of its radiation in the form of ultraviolet or UV rays. Our bodies give off heat radiation. Some radiation is harmless, like the heat from our bodies. Some radiation can be deadly, like ionizing radiation. Ionizing radiation is what we'll focus on here. Ionizing radiation causes damage by attacking cells on an atomic level. Particles and rays have enough energy to knock off an electron from an atom. An atom without an electron has a net positive charge and is called an ion. These ions, also called radicals, are unstable and seek out other electrons from atoms in the body. This can lead to cell and DNA damage, causing sores, cancer, and even death. There are three types of ionizing radiation we'll discuss. The first is from radioactive decay. As an unstable element decays, it releases alpha particles, beta particles, and gamma rays. Unstable elements can be naturally occurring, such as uranium, or man-made, such as certain forms of cobalt. Radioactive materials are said to be unstable because they have too much energy in their atoms. These atoms spontaneously release this excess energy in an effort to achieve a more stable situation. The released energy is called ionization radiation, which, as previously mentioned, has enough energy to strip atoms of their electrons, creating ions. Henri Becquerel first discovered natural radioactivity in 1896. Becquerel put photograph plates in uranium in a drawer. He later saw that the plates had been exposed to light. Becquerel concluded that the uranium exposed the plates. Future experiments showed this radiation had alpha particles, beta particles, and gamma rays. How does ionization radiation occur? Let's look at the nucleus of a radioactive substance. The nucleus contains neutral particles called neutrons, positive particles called protons, and surrounding negative particles called electrons. In ionization radiation, different materials release different particles to go from unstable to stable. Some radioactive materials have too many protons and neutrons and release the excess, called alpha particles. Some materials have too many electrons and release the excess, called beta particles. When a radioactive material has too much energy, it releases photons, called gamma rays. When coming in contact with other atoms, this ionization radiation removes electrons from orbit around the nucleus. Alpha radiation has the most potential for harm due to a more powerful charge interaction with surrounding atoms. The alpha particle can interact with electrons in other atoms from a greater distance because of its stronger charge. The beta particle has less potential for harm due to its smaller charge. It needs to be closer to cause damage. The least potential for harm is the gamma ray that has to have direct contact with an electron to cause damage. Even though alpha particles have the most potential for harm, they are too big to penetrate skin. Beta particles are smaller and can penetrate deeper than alpha, which can damage tissue under the skin. Gamma rays, however, can penetrate deep into the body. Only dense materials such as lead can stop gamma rays. For this reason, gamma rays are considered the most harmful type of radiation. The second type of ionizing radiation is from X-rays. X-rays are photons like gamma rays and can be emitted from radioactive decay, but they are most commonly created in X-ray tubes that can cause the release of excess energy as photons. German professor Wilhelm Conrad Röntgen discovered X-rays in 1895. While experimenting with light and cathode tubes, Röntgen noticed that when he blocked the cathode tube with a piece of black cardboard, something from the tube caused a chemical substance 9 feet away to glow. Further experiments showed this ray was able to penetrate soft tissue, but not bone and metals. Röntgen had discovered X-rays. These photons quickly became a hit in science and popular culture. Only some people recognized the danger of X-rays, and it wasn't until the golden age of radiography, beginning in 1915, that widespread, organized efforts began to limit X-ray exposure and damage. Early efforts to prevent X-ray damage included lead-lined protective gear and even increased vacation time for radiation workers. Over 100 years later, we have developed today's similar standards, including lead-lined PPE in walls, and personal badge monitors for those working with X-rays. With today's regulations, the average American citizen is unlikely to be exposed to X-rays outside of hospitals and health clinics. Even then, the provided PPE and limited exposure time is very unlikely to cause cancer or long-term damage to either worker or patient. The third type of ionizing radiation comes from a source that reaches us all: the sun. German physicist Johann Ritter discovered ultraviolet rays in 1801. While experimenting with silver chloride, which turns black in sunlight, Ritter discovered that the silver chloride reacted more intensely in the area just beyond the visible light spectrum. He called his newly discovered invisible light oxidizing rays. We know this light today as ultraviolet or UV light, the third type of ionizing radiation. The sun gives off many rays, but only UV radiation reaches us. From the Planck-Einstein relation, energy equals Planck's constant times frequency, we know that higher frequency waves have higher energy. UV rays have more energy than harmless radio waves, but less than damaging gamma rays. Some exposure to UV rays is beneficial to our health, but excessive exposure can cause severe damage. This is because of the wavelength of UV light. We know from the equation for frequency, frequency equals speed of light divided by wavelength, that a smaller wavelength means a greater frequency, which in turn means more energy. Longer wavelengths also mean deeper penetration into the skin. UVA are the longest of the UV rays and are responsible for deep penetration into collagen elastin, causing wrinkling over time. UVB rays are shorter than UVA and penetrate the outer layer of skin. About 95% of the sun's UV rays that reach us on Earth are UVA. The other 5% are UVB rays. Even though relatively few UVB rays reach us, they are higher energy than UVA and so account for most skin cancers and sunburns caused by UV rays. UVC rays are the third and most dangerous of the sun's UV rays, but are absorbed by our ozone and never reach us. UVC rays are, however, emitted by some man-made industrial equipment such as plasma torches and germicidal lamps. UV rays interrupt cells by creating ions within the body, which in turn disrupt other cell functions. Prolonged exposure to UV rays causes burns, thickening of the dermis, cancer, and cell destruction. Preventative measures for UV exposure ranges from simply using sunscreen and limiting time in the sun to industrial standard PPE when working with UV-emitting tools. Since the discovery of damaging radiation, protective measures have been in place to limit exposure and risk. Early pioneers of safety and prevention were limited to a few concerned citizens and scientists. But today we have dozens of organizations from local, state, federal, and worldwide agencies who regulate radiation exposure. All of these organizations provide industry-specific guidelines to protect citizens, workers, and the environment from damaging exposure to ionizing radiation. One of the most well-known regulatory bodies is the Environmental Protection Agency, or EPA. The EPA monitors and regulates radiation exposure ranging from inside a nuclear power plant to the air we each breathe. The EPA has also put together 3 general guidelines for the public to follow in the case of a radioactive explosion or disaster: limit time, increase distance, and use shielding. These guidelines form the foundation for all preventative protocol when working with radiation, and though simple, they have proven effective.